So yesterday we did, aside from his instrumental theory and why choose LCMS, we did some hardware coverage. You guys got to be a little familiar with the instrument itself. We did some software introduction, just some basic stuff to get you warmed up. We did tuning, and we learned some things about tuning. We went over what we considered to be acceptable parameters for the tunes. We learned some stuff about the file names, which was a little extra. We weren't actually planning on doing that, but it is a learning experience. It was yesterday. What else did we do yesterday? We showed you guys how to do batches, how to submit samples. We reviewed test mixtures, what we put in the test mix, what we considered to be good indicators of instrument suitability, and why we put those things in there. We looked at some data. You guys actually processed some data yesterday and looked at it. We went through some compound optimizations, so you guys saw how the instrument will generate some data for you for individual compounds, and you're going to use that data to create methods. Mike's going to go over that part today, the specifics about the data you saw yesterday and how that interacts with the method itself. And we injected some quantitative samples last night, very last thing at the last minute, and some unknown samples. So we're going to look at those today. We did have a little problem with the instrument last night. It shut off. But we have re-injected them. They're running right now, so you guys will still have things to do today because we're going to process those. You guys have a whole list of things to do today. So that's what we covered yesterday. We're going to cover some other interesting things today. Like I said before, you're going to do some processing. We're going to show you about quants and some more injections today. So do you guys have any questions for me about anything we did yesterday that you wanted to recover or anything like that? Yes, sir.
We tuned Q1
Yes.
and Q3.
Yes.
Is there a way to tune the trap?
There is a way to tune the trap. You have to use a different solution in order to tune the trap. If we have some time this afternoon, what we talked about yesterday was, since this afternoon is going to be mostly individual processing and it's going to be very fluid and very flexible, if there's anything else that you guys would like to try to cover on the instrument while we have time before our hard deadline of 4 o'clock, we will be happy to do that. So if we have some time this afternoon, we can go over that. Okay? Anything else?
Is it necessary to tune the trap, or?
I think they probably recommend that you do it periodically. I can't remember exactly what the manufacturer suggests that you do as far as that's concerned, but just like the regular tune checks, it's probably a good idea to try to incorporate it somewhere. So, anything else? Okay. Well, now we will be entertained by our host with the most, which would be Mike.
Great. More pressure. So, I guess one of the major things that you're going to do once you've uncrated your instrument and learned how to use the software is you're going to start trying to do casework on it. In order to do casework, you're going to need to build a method that works for you, whatever your processes are. One of the things I want to stress is some of the things that we have in here and some of the things you'll see in our method, those are the things that work well for us. Your applications will be different. Your source pressures will be different. It depends on a lot of the instrumental variables. They are slightly different. Each one's its own little beast and might need a little bit of tweaking here or there. So please don't take a number out of this slide and say, well, it worked. This number worked in this thing, and why isn't it working for me? You're going to have to tweak it for yourself. We have found, though, that we can transfer methods pretty well from one 3200 instrument to another one. So method transfer within our own lab has been pretty easy, but even then, each one of them we tweak just a little bit to make sure it gives us the best result. What I'm going to talk about today are the steps that we went through in building a method, and a lot of the stuff was learned slowly, first by Bill and Hort McCurdy, if you know who he is, and then later by everyone else, and this is sort of the way we sort of teach in the laboratory. Do these things and learn this and then learn this, so that by the time you all saw the method, and I think you're going to get a copy of the method, the idea is in court that you'd be able to know what every DP and EP and CEP, all those things are mean and what they're for, so you can explain them to somebody or say, well, what's that for? Because there's nothing more embarrassing than going, well, what's that? And it's a thingy that works. So the way I break down the method is the source parameter optimization. That's all about getting this solution ion out of the mobile phase and into the mass spectrometer. So those are the little parameters. They're at the very front. Those are the gas pressures and things like that. The next one is compound optimization. Yesterday you did quantitative optimization. That's what I'm talking about. And that's getting the parent ion through the mass spectrometer and selecting the right collision energies in order to smash that molecule into bits and then selecting your bit. The last part there is MS optimization for EPI or product ion scanning. You need to be able to produce reproducible full scan mass spectra with lots of data, as much data as you can get. As many ions you can get means you have a better matching capability. If you only have 3 ions, you have, they're either there or they're not there. But if you have 55 or 100,000 items or whatever, you can start to do a lot of good library matching with that. And then at the end, I'm going to talk about how we link MRM with the EPI using the information-dependent acquisition. You probably have seen a little bit of that yesterday. All right. Yeah.
The MRM, how do you define that?
How do I define that? That's multiple reaction monitoring. That's the big list of transitions, parent to daughter, parent to daughter, parent to daughter. And so that's our survey scan. Does that answer your question? And again, if I start dropping into acronyms, just stop me, because I will do it. Joe knows that I will start talking about P's and EPs and MRMs and EPIs. So, right. What you yesterday when you infused one drug, that's the step you have to go through in order to get the information for one MRM transition, and then you plug that into the method, and it's just one line. And then yesterday when you saw through the information tab, the lines are marching forward. That's all that information plugged in to a stack of MRM transitions. And you don't have to choose one ion. You can actually monitor more than one ion per drug. Depends on what your purposes are. Okay, lots of tiny text here. The turbo spray parameters, the goal is to maximize ion formation based on the liquid matrix. So methanol and water are different than acetonitrile and water, and they will need different things, different temperatures. It's usually set globally throughout the method. We don't change it in time. We try to set the same source parameters and use those throughout the LC program. If you change temperatures and pressures, remember things have got to equilibrate, so you just find a set that works good for you. How do I find a set that works good for you? Find a set that works good across many different types of drugs. In multi-compound methods, it should be generalized. If you're analyzing for 2 compounds, then you can really tailor it for those 2. But clearly, propoxyphene is not going to have the same sort of ideal source parameters as, say, cocaine or something like that. They'll be similar, but not identical. The compound parameters, the goal is twofold. The first is to maximize the parent ion reaching collision cell. In other words, I'm getting my cocaine out of the solution into the mass spectrometer, and I want to get as much 304 ion to the collision cell because that controls how many fragments I will then form. The second is to optimize fragmentation. So suppose I wanted to be maximally sensitive for cocaine, and the transition or daughter ion that I'm going to choose to look for cocaine is 182. Well, I want to maximally produce 182. So that's the 2 goals of compound optimization for MRM. Getting as much 304 to the collision cell and then producing as much 182 as I can, because that's the only thing I'm going to detect. Okay? The MS experiment determines if the parameters are generalized or set globally. Remember in MRM, those DPs and EPs and all that sort of stuff, they're all very drug specific, or they can be. And for EPI, they're set globally. We just don't have the method that this instrument uses does not allow you to tailor those parameters for a particular compound, which is fine, because if you set a set of general parameters and then collect all your information from those general parameters and then build a library within your laboratory, then you can match your unknowns to that library, because everything is exactly the same throughout the instrument. The MS parameters, we're really talking about product ion scanning here. The goal is to optimize resolution and sensitivity and minimize scan time. Remember, the cycle time for the MRM is about 2 seconds. It takes 2 seconds to go all the way through, and then it takes about another second to do the product ion scan in the system we have set up. If you can change things to make those the product ion scan take 3 times as long. And remember, if it takes 3 times as long, then that means you're missing some data while it's doing that sort of information. So more scans across a peak means it's more likely that you're going to get to something lower underneath if the cycle time is faster. Does that make any sense? Basically, you get to start over faster, and so you get to see more information. Alrighty. 2 things you're going to see a lot on this slide. You're going to see infusion and FIA, or flow injection analysis. These are the things that I did when I made a lot of these slides. Infusion is just what you did for compound optimization. You load your sample into the syringe pump and you just inject it, and you tweak the source and record the data. The compounds were in 50-50 mole phase, which was methanol and methanol. Actually, it was mostly water. I'm sorry, it was water with just a little bit of mobile phase in there. I put the mobile phase in there to make it slightly acidic to promote ionization, so that I would get a nice strong signal. For flow injection analysis, I left the syringe was still there, pumping, but then I also added through that little T. You see the little union where you tighten in the LC effluent to the source? You can actually take that T out there and put a union that will allow you to T in the flow from the LC as well. And so what you're going to see is the difference between infusion and flow injection, or what is the difference between just infusing the drug and then having the drug come out with your mobile phase, because they're going to be different, and you're going to see how different they can really be. So the turbo spray settings. Turbo spray is Applied Biosystems' way of saying electrospray. It's turbo because it's got the gas and it's heated. The parameters are the ion spray voltage, the nebulizer gas, the hair dryers both have two parameters to set them. One is the temperature, one is the heater gas, which is GS2, which is just basically how much that's flowing out. And then the curtain gas, and there's another parameter in there called the interface heater. We just leave it on, and there's nothing to optimize on or off. We choose to leave it on, works fine. Here's your overview of the source again. You remember where everything is, where the GS1, the temperature, ion spray, the heater, and the curtain gas are. I've kind of color-coded to sort of give you an idea which ones are temperatures, which ones are voltages, and which ones are pressures. Okay? So let's look at the ion spray voltage here. And what you're going to see is this top line right here. This is the one I really want you to pay attention to. The bottom line is a flow injection, or this line, I'm sorry. This line is a flow injection line, and this line right here is an infusion line. And what you can see here is that at 1,000 volts, when I set the sprayer to 1,000, the reason you don't see in here is because that number is like 0. It's like 4, 0, 2, 0. There's nothing there. 1,000 volts is not enough to extract ions from the droplets. The droplets are being formed because I've got gas flowing, or I'm nebulizing. Stuff is being squirted out of the needle, but there's not enough voltage to extract ions. You can see when I increase it to 2,000 that I get all of a sudden, it's just on, and I get, was it 5e to the 7? Or I'm sorry, it's down here. 3.5 e to the 7, and then about basically double that by the time I go to 4,000 here. And then I add a lot more when I go to about 5,000. Not much difference between 5,000 and 5,500. At that point, you're not really gaining a lot by going the little extra mile, but 5,500 is where we run it. But you can see the huge difference between 1,000 and 2,000 and 5,500. So ion spray voltage makes a difference. We set it basically as high as we can set it without having something bad like some sort of discharge going on. Part of the reason one of the nice things about having that bath gas that fills the whole turbo spray chamber is it actually suppresses discharge in there. And they tell us if you're having a problem, look inside. If you see a blue glow, you're having a discharge. That's bad. In electrospray, it's bad. In chronodischarge or APCI, it's fine. But for the purpose of electrospray, it's bad. The bath gas or the turbo spray gas in there sort of gets rid of that. But if you see it, it's all bad, stop, call your service rep. Nebulizer gas, GS1. This is the gas that flows around the capillary and squirts out, helps to form spray at liquid, helps to facilitate the droplet formation at LC mobile flow rates. You can see with an instant infusion, I don't really need much of a gas pressure here. You can see that about 20 psi pretty much maxes out, and then it drops down. And you can see at the bottom that doesn't look like a big difference, and it probably isn't too much of a difference here. But you can see that by the time you get to about 50 psi, it is you definitely get more ion formation than you do down here. So it goes from about 1.2 e to the 7 up to about 1.7 e to the 7. That's the maximum thing on there. That's a little bit. Every little bit helps. But you can see that if you increase it too much, you actually start to cause more problems than you solve. So you can see a little bit the difference there between infusion and flow injection. Infusion, remember, that's sort of your ideal situation. Flow injection is real sample coming off in a real LC program. Okay, so the bottom one is best reproduces what's happening when your sample's coming off the column. All right. Temperature, and here's where you're going to see a huge difference between just no temperature. I don't need that. I'm concerned that my drug might fall apart because of temperature. You don't need to be that concerned because the volatile mobile phase is coming off, and that's what's keeping things cool for your sample, for your analyte. And it pops right out of the gas into the gas phase and gets sucked right into the mass spectrometer. You can see on this side infusion, there is a difference between a temperature off here at 9 e to the 7 and here at 1.3 times 10 to the 8th, which is a lot. But you can see a huge difference, a 350% increase from here to here. So you can see that temperature makes a difference. Why does temperature make a difference? Remember, the middle stage in ion formation is what? Desolvation and droplet fission. Driving this heater, turning the heater up in there, helps that mobile phase, methanol water, leave. Your volatile buffers are leaving the droplet's shrinking faster, and when it shrinks, it breaks apart, and you get your little ions, your small droplets, and they shrink, and then your ions pop off the surface. Putting the heater up facilitates doing that. We don't run it much above 500. You can see there's not much gain between 500 and 600, but 500 is about where we max it out. Alrighty, gas 2. To be honest, gas 2 is how much pressure is coming out, how much gas flow is coming out of the hair dryers, and you can see it's pretty flat. It tends to go, and this is the FIA. This is FIA right here, and this is just the bottom line here is GS1 is set to 10, which is the nebulizer gas, and the GS2 is set to 0. This is the difference between having it on and having it off. And you can see here the pressure doesn't really matter, even though it does tend to go up just a little bit and then goes suddenly down. I think this area, this is just me talking, I think this area right here, the source becomes very turbulent with a lot of gas in there. But you can see that makes a difference. Not that much difference between 20 and 50. We run it somewhere in the 50 area. All right. The curtain gas, don't really have a graphic for curtain gas because there's not much to say, except for the curtain gas should be maximized to repel nutrients and droplets without dramatically impacting the sensitivity. In other words, if you're tweaking your curtain gas pressure, what you want to do is increase it until you see your sensitivity start to really drop off, and set it there. The geometry of the source that you saw in there yesterday, remember the sprayer is coming down at a 90-degree angle to the plate right there. So the sprayer is actually spraying straight down into the waste, and the ions are actually making a 90-degree turn into the mass spectrometer. Some other older instruments, especially the older instrument that we have, the sprayer's like this, which is why, like day one, I'm spraying it right into the hole, and so that's bad. Curtain gases have got to be higher for an instrument like this than they do for an instrument like that, and they make a lot more. They make a lot more difference in an instrument with this sort of geometry as opposed to an instrument with this kind of geometry. The Mobile phase composition and flow rates affect the source parameters. Remember, we talked about yesterday, if you increase the water content, this will require a higher temperature and gas pressures. Water is a little bit less volatile than methanol, so you have to increase the temperature in order to get more ion production. If you're running a system like ours, we start out at 95% water and we end up with 95% methanol. So we sort of set the temperature so that we're dealing with that water at the beginning, and then at the end the methanol is just evaporating quickly. Increasing the flow rate will also require an increased temperature and gas pressure. Remember, if you start increasing the flow rate too much, the first thing that's going to happen is the droplets are going to get bigger because there's more fluid coming out of the end and it's breaking off sooner. So you get bigger droplets, which means you got to increase the temperature so that you can shrink them down. And it's only by shrinking them down that the ions get crowded together on the surface and they have enough energy to just go boink into the gas phase. And that's what you're really trying to get after for electrospray. Using a flow injection analysis reproduces the mobile phase conditions at compound dilution and helps to maximize sensitivity. We did the flow injection at 50-50 mobile phase A and B. If you are looking to maximize a particular drug that comes off at a particular time, and you know what time it comes off, then try to reproduce those mobile phase conditions to maximize its particular sensitivity. So if you have a one drug method or two drug method, you can actually tailor your FIA to be specific for the mobile phase conditions at the time of elution. Just a thing to think about. Probably won't make that much difference, but if it's the difference between seeing it every time and seeing it most of the time, you know, every little bit can help. The instrument method that we've created is one for 130 drugs that come off from the very first minute to about 18 minutes. So we just generalized for everything. Okay, so now you have a beautifully optimized source that's both general and optimized. I mean, that thing is producing ions. So the next thing you need to do is start infusing your drugs and picking your compound parameters to put in your MRM transition method. And the first thing you do is to select your mass. It needs to be the exact mass of the most abundant isotope. So if you're like me and you're used to be honest, I look things up in Wikipedia all the time now. And it has sort of a general mass in there that's based on, you know, the average isotopes. Just go ahead and not always think about that. You need to actually plug in the molecular formula and choose the most intense exact isotope mass. Does it make a difference? 95% of the time, not really all that much, but sometimes it really does. There's a few drugs, and I think I want to say it's lamotrigine, I think, or is it loratadine, where actually the average mass is off from the exact mass by 1 AMU, which means you're going to be optimizing an average, which doesn't really exist. So make sure you put the exact mass of the most abundant isotope in there. The second thing you need to do is optimize the compound voltages to maximize parent ion production. And that is what the declustering potential, the entrance potential, and the collision cell entrance potential are for. They're all about getting the parent compound, cocaine 304, from the source to the collision cell. And when you saw compound optimization yesterday, you saw that it was working through the DP, the EP, and the CEP. And at the end, it showed you a beautiful little graph of what the parent compound looked like. If you did cocaine, it was one peak and then a little hump. Does that sound familiar? Cast your minds back through the sleepy haze of early morning. That's what you were seeing on the screen when what it does is say, okay, you want 304, let me grab 304. Okay, let me tweak all my little parameters. How about that? And what it's done, the little parameters that it's tweaked is DP, EP, and CEP. And then you need to optimize compound fragmentation, select an optimized transition masses. So you saw it, remember you started to fragment your mass and you saw the little ions creep up. And then it chose 4 and then optimize each one of those. That's the next process that it goes through. And what it ends up selecting for each one of those is the collision energy that best optimizes that particular collision energy, that fragment production. And then it optimizes collision cell exit potential, which is kind of almost always 4. Sometimes it's not, but it's pretty much always 4 on that instrument. And the last thing is, I guess I've written on here, the quantitative optimization is the instrument's automatic feature for doing that. It's the routine that it does. You plug it in, you enter the exact mass, 303.2, go. And it does it, and then it tells you it's too concentrated, and then we have to stop and dilute it and then do it again. But that's the instrument's automatic routine. If you see that, if you're doing it on your own instrument, and you watch what's going on at the bottom, either the little voltages will change. You'll see what's happening with the DPs and the EPs, and then the CEPs, and then the CE. So that was really confusing, but I'm going to show you each step. Declustering potential, entrance potential, collision cell entrance potential. Getting ions to the collision cell. That's 304 to the collision cell. The collision cell is Q2. It's an ion pipe filled with nitrogen gas. Controlling fragmentation is the collision energy, and there's also another setting called CAD gas setting. If you saw me mention that yesterday, we set it to medium. It makes a difference depending on your application, but somehow medium is always just right. Collision cell exit potential there is not really going to talk about why, because it's usually 4. And the collision cell energy, or the collision energy spread, is a way to, when you're doing a fragmentation for library matching, it's a way for you to do 3 different energies summed together so that you get a nice sort of general mass spec. And we'll touch on each one of those. All right, so one of the questions I had when I first started is, okay, well, what's a DP and where is the DP happening at? Where am I setting that potential? Where am I setting an EP? And an EP, remember, is the entrance potential, and it's all other voltages after EP are more or less based on that voltage. So whatever you set there controls the collision cell entrance potential, CEP. It also affects the collision energy and also the collision exit potential. So even though you set it as -4, it's actually relative to everything else. So it's -4 relative to the next voltage. And I've kind of drawn on here how they're related to each other. So if they have arrows connecting, they're related to each other. And you can see that somehow everything gets connected to entrance potential. CEM is just the setting for the cascade electron multiplier. And that can be tweaked in your instrument just by infusing it and changing the collision until basically you don't see any new change. So you will need to optimize your collision, your CEM, but that's sort of a separate thing. And done once probably a year or so. Declustering potential is the potential applied to the orifice plate. It has the greatest effect on the amount of declustering in the orifice region of the interface. That is in quotations because I pulled it right out of the help file. Because I thought, what is DP? Well, that's what it is. The working range is typically 0 to 100, although it may be set higher. The question I had was, so what am I declustering? What's happening is sometimes your molecular ion gets tied up with some hydronium ion, or maybe some cation that you don't want, or maybe some sort of weird combination of hydrogen and mobile phase. What you want is M plus H. That's it. You don't want M plus mobile phase. You don't want M plus hydronium. You want M plus H. Tweaking the declustering potential, applying a little bit of potential. I kind of think of it as, if you've ever seen a pickup truck that's overloaded with stuff in the back, if you're from Georgia, it's like watermelons or something. It hits a speed bump and some stuff comes flying off. That's what the sort of the declustering potential is. It's a little speed bump that your ion hits to knock off anything that might be there. Unfortunately, if it's set too high, it can actually fragment a compound in the source, which is great if you're doing LCMS, but it's bad if you're doing LCMS. Because in LCMS, you want the fragmentation to occur in the collision cell and only in the collision cell. So what I did here was I infused cocaine, which is one of the joys of being a forensic scientist, is I've handled more cocaine legally than anyone else that I know. And I infused cocaine, and you can see that the infusion had greater sensitivity than the flow injection analysis. But remember, electrospray works best at lower flows, so you're going to get a little bit less sensitivity. But the key thing I want you to notice here is that, one, that the DPs, the declustering potential, the maximum here and the maximum here are about the same. So you're not really losing a lot by optimizing the declustering potential in infusion. Alrighty. What I wanted to show you is what is the difference in result if I examine what's happening in the instrument at 3 different declustering potentials. So I took one, I set a cocaine declustering potential of 20, and here is about the maximum, about 40, and over here is about 80. Okay? So what I'm going to do is I'm going to say, okay, well, let me do a Q1 scan, which is a mass spectral scan, a full scan of everything that's coming into the source while I'm infusing cocaine at those 3 declustering potentials. What happens is, it's maybe a little bit hard to see here. The first column here is that the declustering potential is set to 20. You can see that the ion intensity is 3 to the 9th, and what you see right here is almost all 304. Not much anything else down here. It's actually just, dare I say, garbage down here. This is just random mobile phase stuff coming in. When I set the declustering potential at 40, you can see that I'm actually increased by a third up to 3.3 times 10 to the 9th. So I've got more sensitivity, right? I've got a lot of 304. So this is the most amount of 304. But you can see a little 182 has started to sneak in there. What's happened is I've maximized 304, but in maximizing 304, the declustering potential is actually set high enough now. It's actually fragmenting the ion in the source. So my truck full of watermelons has hit a bump just high enough that a lot of stuff, like a tire or a hubcap, has just flown off. The next one down here is a declustering potential of 80. You can see here's the 304 here. The highest mass here, it says 3.4 times 10 to the 9th. Well, that's higher than the previous one. Yeah, it's 182. I've actually cut 304 down to 1.8 relative to this 3.3. So I've actually now cost myself sensitivity in cocaine. And you can now see there's a 105, there's an 82, there's a 150, there's a 272 underneath my mouse button there. Let me clear that up a little bit. You can see here's a, oh dear, there's a 272 right there. This is starting to look like the cocaine mass spec that I expect in full scan. This is sort of in-source collision dissociation right here. If you're using LCMS, this is probably what you're using. You're actually using something very similar to this to produce fragmentation for you to analyze whatever's coming through the source. So you can see from here, this gave me great sensitivity for cocaine with just a little itty bit of fragmentation. And by here, I'm costing myself sensitivity for cocaine, right? And not only is the hubcap flown off, I've lost 2 wheels and all the watermelons. So we were talking about detuning. If I wanted to detune the instrument for cocaine and make it less sensitive, one of the things I could do, other than select another ion, is actually move around the declustering potential. You can see if I move it to here, I actually lose 50% of my cocaine coming into the source. Okay. Moving forward. Entrance potential. The entrance potential controls the the voltage on the Q1 the Q0 region of the mass spectrometer. Remember the Q0 region? It's an ion pipe. It just passes lines from one end to the other. It's got a little bit of gas in it because it's so close to the opening of the front of the mass spectrometer. When I say it's really close, there's like 2 little thin pieces of metal, and you pull those off, and there's these 4 wicked-looking quadrupoles sticking out at you, and they're all hollow. If Carl would hear, he would be appreciated. I just used the word wicked. It's typically set around 10 volts for positive ions or minus 10. To be honest, typically set means, we kind of default sometimes to 10, but 4, 8, 7, they all seem to work fine. But they do affect the voltages for all other settings in the instrument. And you can see here that both in Infusion and FIA, it's kind of pretty flat from this point forward. So you can see down here it makes a difference. So if you have very low voltages down here, let's say less than 2, you're cutting your sensitivity. But after about 3 or 4, it's pretty flat. So setting it to 10 here is about the same as setting it to 5. So collision cell entrance potential. This is the parameter which controls the collision cell entrance potential, which is the potential difference between Q0 and IQ1. Oh my God, I've just said IQ1. What does that mean? It's inner quadrupole lens 2. What does that mean? It's a little teeny plate of metal with a hole in it right before you get to the second quadrupole. It focuses ion into the collision cell. You know, if you're used to mass spectrometry, there are quadrupoles in lenses. The whole purpose of a lens is just to focus ions into the next quadrupole. And so that's where the collision cell entrance potential is at. It's set there to make sure just that last little focus of ions right into the collision cell. It's generally the most mass dependent. If you don't really optimize this parameter, the instrument will optimize it for you, and it will calculate a collision cell entrance potential based on the mass. And you can see here that for cocaine, it's sort of topped out here at about, I guess that's about 15.5 volts. And for flow injection and infusion, it's about the same. And remember, this is a graph that you would have seen yesterday. You would have seen it go up and then down like that. Does it look familiar? Okay. By the third time you've seen it, it starts to get actually a little boring. All right. So any questions about getting my ion out of the source and into the collision cell? Anything? All right. So now I've gotten lots of cocaine into my collision cell, and now I'm going to start fragmenting it. Actually, what I'm going to start fragmenting is dextromethorphan, because I'm getting tired of talking about cocaine all the time. What we're going to talk about is collision energy and CAD gas setting, and then a little bit about collision energy spread. And I'll probably flip-flopping back and forth between dextromethorphan and cocaine. All right. What is the collision energy? It's the fragmentation of the parent ion is caused, again, by the collision with low-pressure nitrogen in the collision cell. The more energy, the greater fragmentation. So if your collision energy is 80, you're going to get more fragmentation than if it's 10. Seems sort of obvious. But it seems obvious to me now. When I started, I was like, well, okay, whatever. Higher number must be better. No, not really. The collision energy, the energy of that collision is controlled by the collision energy setting, which is CE. The voltage, it's really the difference between Q2, which is the potential on those rods, and the voltage on Q0. So you can see how EP, entrance potential, again, is related to every other voltage in the instrument. And it can be optimized for each drug, and that's called quantitative optimization. That's something you guys got to do yesterday. Higher collision energies result in greater fragmentation of the parent molecule. And I want you to consider the example of dextromethorphan. Now, yes? RO2 is actually, it's called rod offset 2. And rod offset 2 is the interior technical term for voltage on Q2. So the reason why I chose dextromethorphan is once I was creating a presentation, and my boss's boss's boss, the director of the laboratory, is looking at it, and he goes, "Oh, this says the transition for dextromethorphan is 272 to 128. I don't see any 128 here in your product 9 mass spec. It must be wrong." And so, being confident, I went, "No, that's not wrong." So I went upstairs and checked, and I knew that I was right because I often think that I am. And so I went back. We actually went back after that, and I created a set of slides, which I've used over and over to explain collision energy. And what you're going to see here is a series of images that are going to be dextromethorphan fragmented at increasing collision energies. And what you're going to watch is a procession of ions move from high to low. So at 10, very little fragmentation, just basically 272, which is right here. At 20, you're seeing a few more ions pop up right here, but basically pretty much just 272. At 30, oh, well, you know, there's some ions right there. If I needed to, I could call that if that's what I always saw, but I'd really like to see more ions than that, wouldn't you? I would. So you increase it to 30, there's a lot more ions. You can see 272 is no longer the baseline. We've actually, 147 is now the baseline. And you note there's no 128 in here at all yet. 40. 272 is now just a blip. I've got a lot now. 171. It's interesting between 40 and 50. 147 is almost it started to go down a lot. In 171, and there's still no 128. 60. There's a little 128 appearing right there. Still lots of 171. I've lost all of my molecular ion. It's all gone now. 70. Now 128 is now the baseline. 171 is dropping down. 80. 90. And there's 100. You increase the collision energy, you're literally blasting the molecule in smaller and smaller bits. The thing about small bits like this is the smaller they get, the more similar they are to every other compound small bits. So what you'd like to do is strike a balance between this and that and that. And that's how collision energy spread will work for you. So I'm going to go through these really fast because it's cool. So here it is, 10 to 100. And that's the effect of increasing collision energy on a molecule. Some molecules will disappear after the 30 or 40 collision energy volts. There's nothing to see. It's all moved off. It's all down at the bottom. It's all 91s and 44s and 50s and things like that. Dextromethorphan's great because it gives you collision, it gives you fragmentation all the way up to 100, but a lot of them are totally obliterated by the time you get to 50. An MRM screening is generally a single transition is selected for each drug. Why? Because I want to stack 130 of these things together, and I can't really. I need to choose a transition for dextromethorphan is 272 to 128. That's the one we've chosen for a lot of our applications. The sensitivity of the method is directly tied to the or is proportional to the intensity of the fragment ion. So remember, let's see, about right here. This is 128 right here. This is the only ion that's reaching the detector in MRM. That's it. So how much ever of this I can produce controls my sensitivity. So if I wanted to set 80 as my collision energy, but I wanted to detune or reduce the sensitivity of dextromethorphan, I could choose, say, 141. Oops. Oh, dear. I could choose 141 or 115 if I wanted to. You can see how I'd be cutting sensitivity by choosing a different ion. All right. Back again. So the question is, how do you select a transition ion to monitor? One of the things you want to do is you want to pay attention to the uniqueness of the transition. And so you want to pick an ion that pretty much at 272 to 128, only dextromethorphan is going to cause that. You can be reasonably confident of that because after you've seen about 50 100 real blood cases go through and only dextromethorphan has triggered it, you're like, phew, I did good. But if you had selected, say, 91, which is a really common fragment, you might actually see some other stuff trigger that transition. Why? Because it fragmented in the source a little bit and might actually trigger the transition. So you want to pay attention to uniqueness of the transition if you can. And a good way you get a feel for uniqueness of transition is to infuse 130 drugs and see which are the usual suspects that keep popping up. What are the product ions, transition ions that keep showing up all the time? 91 is one of those. So quantitative optimization, again, starts with a compound optimization, then it fragments the parent mass at many different collision energies, and it picks the foremost intense ions, but you want to avoid the loss of water, which is why you basically choose a fragment with a mass shift of greater than 19 AMUs of the parent. And you determine the collision energy that produces the maximum amount of each transition ion. So remember that 10 to 100 I just did there. What I did was I added all those together. I actually summed the mass spectra up. And you can see that this is kind of what it looks like when you actually add them all up. You thought, well, I saw lots of tall ions before. What happened to them? Well, when you add them all up, some of them actually look more like grass than the tall ions. You can see 272 is very prominent through the first, say, 30 volts or so, and then it dropped off. So there's still lots of 272 even if I add 10 to 100. And what I want to do, I've already maximized 272 by getting it to the collision cell. What I want to do is optimize 3 fragments. And so these happen to be these 4 fragments. These happen to be the 4 most intense fragments when I was doing this work. And what the instrument does I think I've overlaid these. And I'm sorry, this is going to be a little hard to see, so I'll try to draw over it with the magic pen. You can see that 128, which is the ion that I've chosen for a dextromethorphan. Oh dear. I have to push the other button. All right, here we go. Here's 128. So you can see actually at this moment in time, it's actually not the most intense one. 171, which is this line right here, is the most intense, but 128 is the one we use. There's not really that much difference between this one and this one, actually. It's only 1 e to the 7 or 1.4 e to the 7. That's more than enough sensitivity for dextromethorphan. What you can see at the bottom here is the march of collision energies from 10 to 100. So here's 100. And you can see that, even what you saw there, that 128 is maximized from 80 or 90 volts, somewhere in there. It actually maximizes about 83 volts. 171 is about 50. 147, that was another fragment that I chose to look at. It's about 40. 215, it's a higher mass. So remember, 215 was maximized early on. You actually remember, when you go back and look at your slides, you'll see that let's say about 30 volts or so. That's where 215 was maximized. So if I wanted to choose 128 to 215, I would set it at 30. If I wanted to choose 128, I would actually set it to about 84. So now I found the collision energy that best produces 128. Okay? That's what building an MRI method is all about. If I wanted to detune the sensitivity, I could choose 215. That would cut it basically in half. If I wanted to detune it even further, I could go back and try to optimize one of these other smaller masses if I thought it was specific enough for dextromethorphan. All right. So, any questions about selection of a transition ion to put it in your MRM method? Any questions?
You chose 128 because it was unique and then optimized. That's sort of what we're saying.
Right. We actually did dextromethorphan on the first instrument we had, and 272 to 128 was the one that worked fine. It's the one that worked the best, and it was very specific for dextromethorphan. We did the infusions on other instruments, and sometimes 171 would be a little taller, and sometimes 128. To keep the instrument methods all the same, and because the 3200s are so much more sensitive than the older Q-trap, we just said, look, 128 is buying us just about as much as 171. So to keep the methods the same, so that processors don't have to have as many ion transitions in their head as they could. 130 times 4 would be a lot. We kept it the same. Gave us plenty of sensitivity.
What's your final setting?
128. 272 to 128.
180.
Oh, ADC for your C.
Oh yeah, it's around 80. Actually, if you go just a second, I'm going to show you the actual MRM. Remember the march of methods you saw yesterday? I'm actually going to show you what we ended up with.
Quantop, right?
This is not by Quantop. I actually did this by hand, but in Quantop is just is the way to do it automatically. This is actually me doing it by hand. As Lisa said, it's a teaching tool, and but this is what the instrument does for you, and it takes 15 minutes or something like that. It takes about 15 minutes. So you can see, we had a little race in the lab to see who could get the most done in a day, and just squirt and check, go to next one, squirt and check next one, and then we got all the paperwork, and then started to collate and look at one method and compare them all together. That's the process you will go through. It's a long process, but it's one that once you're done with it, you're done with it. It's in the method, it works. The dwell time is the amount of time the instrument spends on a particular transition. Remember, a transition's parent to daughter. Dwell time is the setting that says how long do I want to spend looking for this parent to daughter transition. It affects the sensitivity up to a point, but decreasing or increasing the dwell time above about 50 milliseconds produces little, if any, additional sensitivity. And for most of our drugs, a setting above 25 has a little or no effect. A longer dwell time also lengthens the total MRM scan time. Remember, the MRM scan time, MRM is just parent to daughter, 10 milliseconds. Parent to daughter, 10 milliseconds. If you made them all 50 milliseconds, that would be what? 5 times longer, which means my 2-second scan becomes 5 times longer, it's 10 seconds. So that's a thing you need to think about every time you increase the dwell time. You're increasing the length of time that it takes to do a scan. What I have found, and I say I mean the GBI crime lab, including Lisa, it's sort of a royal I. If you look at dwell time here, and intensity here, so this is the total kind counts, what you're going to see if this is 1, 2, 3, 5, 10, what you're going to see is it's going to kind of go like that. And so, and this is for most drugs, not all drugs. As you increase the dwell time, you're going to get some sensitivity increase, and it's going to kind of flatten out. Where it flattens out depends on the drug. We have some that do this. Couldn't really tell any difference in sensitivity. And we actually had one that went like that. So I don't know what to make out of that. What we took out of that is 25 seems to be the most we're ever going to make it if we want to increase sensitivity, and we don't really drop it down much below 1. All right, and actually, if you set a dwell time of 1, it actually spends more time pausing before and after that mass than it does actually analyzing for it. But if you're trying to overcome the supersensitivity for caffeine, that's one of the things that you can do. All right, so building your MRI method, we've optimized our source parameters. Yay! That's your DP. That's your gas parameters. You've optimized the compound parameters. That's the DPs and the EPs. You've selected a 9 for fragmentation. You've selected a collision energy for that fragmentation, and you've done this 130 times. Now you're ready to build an MRI method, and what you end up with is a panel that looks just like that. This is dextromethorphan, the parent, the daughter. We don't spend very much time looking for it. Why? Because we just don't care that much about dextromethorphan in post-mortem cases unless they've been taking a lot. And trust me, 1 millisecond is plenty sensitivity for dextromethorphan. So we still see it at a fairly low amount. You can see that it has its own declustering potential, entrance potential, collision in cell entrance potential. And for the actual MRI method that we're using, you saw that in my hand method it was 84. You can see here it's 81. Those are basically identical. And the collision cell exit potential is what? 4, because it's pretty much always 4. Any questions about that? Basically, in the method editor, what you do is you type all those numbers in. What you really do is you have somebody read them out to you, and you just type them in. Or use the sort of Excel clip-ins feature that it has in there now, which is really nice but wasn't there originally. Alrighty. So MS parameters. This is enhanced product ion scan. Remember, enhanced just means you're using the linear ion trap. The gas parameters are global, which means they exist throughout the method. But the collision cell, the DPs and the EPs, those compound optimization parameters, they're global as well. How you set them globally depends on your application. We kind of sort of averaged ours together, and we kind of sort of came up with something that really worked. And once we knew that we worked, we went with that. We also set up a collision energy spread, and we applied that collision energy spread to every single compound and built a library off that. And we set a collision and gas pressure of medium, and there's some LIT settings like fill time, scan speed, and Q0 trapping, which I'm going to show you a little bit, but not too much. So here is dextromethorphan. You recognize this again. This is very similar to that sum scan you saw before, only this is an enhanced product ion scan, where I set a collision energy of 20, and I did a collision energy spread of 30, which we believe is 10, 20, 50. Does that make sense? The spread is 30, so it's plus or minus 30, but we don't think the instrument goes below 10. So we think it does 10, 20, and 50. Make sense? Then it takes those 3 voltages, it takes the result of those 3 collision energies and adds them together, and you get this. And what you see here is you see a big 272, but you see lots and lots of ion detail. This is the kind of detail that includes both high masses, so there's that 215, remember? And also low masses, and you can see there's no 128, and this is why the director of laboratory went, gotcha! And I went, oh no, we got this covered. But you can see there are lots and lots of masses here. And I can use that to make a library match, and I can call that dextromethorphan every single time. The source settings are set globally. They're basically set that way for the mobile phase LC program. The compound parameters are individualized for M or M, but must be set globally for EPI. So here's all the ones you have to set globally. And the goal of EPI optimization is to find the best settings to produce the best MS data that's reproducible and library searchable. You don't want to have sort of willy-nilly settings. You want to basically set up your parameters that work well. In our case, we have 130 drugs. So we have to find a set of parameters that work well for 130 drugs, not for just cocaine. If I have a two compound method, then I can optimize parameters for that. But they may or may not match a library that I built using more global parameters for 130. The reality is that these parameters will work really great for most compounds. They will not work so great for some compounds. You have to take the hits where they come, but once you know where they are, then you can deal with those as you go. Okay, you see quotations here. I love the help file. The collision energy spread parameter controls the spread of collision energies used when the LIT fills. It is used in conjunction with the collision energy, so it's based on the collision energy sort of that you set, so it's 20 plus or minus 30. By specifying the collision energy and the collision energy spread, low, medium, and high collision energies are used in a single scan to provide maximum information in the product ion spectra, low and high mass fragments. That's directly out of the help file. I love the help file. We've chosen 20 plus or minus 30. You can see or 25 plus or minus 30. What we did there, we had an instrument that just needed a little bit more gas in order for gas. I mean, not pressure, gas pressure. I mean like pedal to the metal. You need just a little bit more voltage to get a little bit more fragmentation so that it better matched the library. That's how we tweaked it in our lab. It provides the best fragmentation across the widest number of drugs. So I wanted to show you here collision energy of 30. It's really 10, it should be 10. I think this is a 10. It should be 10, 25, and 50 there. And the bottom was at minus 30. You can see there that the one at the bottom doesn't look nearly as good as the one at the top in terms of the intensity of these ions right here. And that really has to do with the way the instrument works. Remember the instrument, we're using enhanced product ion scanning. The instrument actually fills, the trap fills. It stays open for a set period of time, say, let's call it 50 milliseconds, right? Ions actually have to get from the front to the back. And so if I start at 10, I've got a little bit of ion, a little bit of 304 coming through, and it comes through and it gets fragmented to 10. But just a few milliseconds later, it's already switched to 25. But now I've got more ions coming through. So I get more fragmentation of those ions. Why? Because there are more of them in the collision cell. And then just a few milliseconds later, it's already at 50, because it has to do the 10, 25, 50 all in the fill time of the trap. And so at the end is where I have the most number of ions, so I have the most amount of fragmentation. And so it's also at the highest collision energy, so I see a lot more of these fragments down here if I go lowest to highest. Now, is that making any sense to anyone? Basically, the instrument releases a burst of ions. You can imagine a big cloud. And what happens is the leading edge of that cloud gets in there when the voltages are really low. And the back bulk of that cloud gets in there as the voltage increases. So as the voltages increase, I get more fragmentation, and I have more ions, so I get more sensitivity for those low ions when I run it low to high than when I do if I run it from high to low. Make sense? You know what I would say? When you get one, try it out. See what happens, works for you. This is what I did. I was surprised by this result. When I saw that, I went, what? Well, I have to figure that out. Oh yeah, totally, I got it. And it is because it's releasing impulsive ions. The collision gas pressure, the CAD gas, is the pressure of the nitrogen gas inside the collision cell. We use the simplified mode setting, low, medium, and high. It runs about 3 torr, 3 times 10 to the minus 5 torr in medium. These are the actual settings for the instrument the day I ran some of these experiments. So I just wrote them down and put them in here. The collision, that collision gas also helps to cool the fragments and focus them into the LIT, so it serves 2 purposes in one. It actually fragments and also cools so they get to the collision cell, or get to the Q3. And you can see here are the 3 different CAD gas settings. Low, I still get plenty of fragmentation at low, medium, or high, but you can see at high and medium, the base here is 1.4 times 10 to the 9, and this is 2.4 times 10 to the 8. Let's put it 10 to the 8. Does that make sense? Can y'all read that? No. I have chicken scratch and everybody complains. The thing here is, when I fragment mine, my fragments now have energy and they're going everywhere. The pressure of gas in there helps to cool those, take some of the energy away, which allows the quadrupoles to then focus them back into the analyzing quadrupole, the LIT, right? So if I don't have as much gas, what happens is some of the fragments they just get lost. They got so much energy they go outside the rods and they're lost forever. They get sucked out the back. And you can see that by setting the CAD gas pressure, I get about the same amount of fragmentation for all of them, but I get more intensity if I set it at a higher pressure. Again, I didn't realize, I sort of kind of knew this and they sort of told me this, but I didn't realize it until I actually sat down and did this experiment. That's cool. We had it at medium already. We were fine. Alrighty. The linear ion trap. So now I'm switching from the collision cell into the linear ion trap here, and I'm talking not as a product ion scan, but as an enhanced product ion scan. It has a couple of important settings. One is the mass range. Well, clearly, we scan 50 to 500. If you scan 50 to 1,000, it would take twice as long because it has to scan a larger mass range. The scan speed is how fast it scans. 250 here. Oops. I have to press the righty button. 250 gives you better mass resolution. In other words, I can separate 303.3 from 303.5 or something like that. But we set our scan speed at 1,000, gives us roughly unit resolution, and it covers the entire mass range, 50 to 500. How fast? Half a second. If you scan it to 250, set to 250, it takes 4 times longer to scan the same set of masses, which means the time it takes to produce an EPI spectra is longer. But you'll get better mass resolution. If that's what you're after, then it works fine. You can see here the 3 different scan speeds. Our instrument is really optimized for 1,000. So there's not much difference between 1,000 and 4,000 for us. But if you look closely here, you can see how resolved 309 and 310 are. They're resolved all the way down to the baseline here. So that's what you buy. That's what you buy for yourself when you set it to a slower scan speed. You get better mass resolution. These ions, 310, 309, 310, and 311. This is actually from Alprazolam. These are all resolved from one another. Whereas here, for at 1,000 AMUs per second, you can tell the difference between 309 and 310, but you can see that they're not baseline resolved. Most of us are, if you're using GC, you think of masses as lines on a graph. And that's it. That's, what is that called? Centroid, that's right. We think of things as being centroided, which just replaces this line with this sort of peak with a line. But this is how the instrument produces mass spectral data. And you can see the difference between 250 and 1,000 and 4,000 by the increasing resolution of masses as I decrease the scan speed. Remember, it's an ion trap. Resolution is controlled by the speed, and that's it. Any questions about that? All right. It also has 2 more settings. One is the fill time. That's the amount of time the trap remains open to accept ions. It can be fixed, for example, 50 milliseconds, or dynamic, which is called DFT. Remember I talked about space charge yesterday? Space charging can occur when the trap overfills. That's less of a problem with this linear ion trap that's really big. But it can be a problem if you're, if you're in the chemistry section and you dilute and shoot, which you have a powder and you make a solution and you inject it on the LC and you go, oh my gosh, why did it shift? If you're in tox, everything's real tiny to begin with, and so we don't have this problem as often. But if you were to have it, one way the instrument could do it is by altering the dwell time on the fly. And the way it does that is by pre-sampling the peak and says, okay, I'm going to take a peek at this peak coming in here, and I'm going to see how many ions I'm going to produce. And it says, okay, that's a lot. Let me reduce the dwell time so that I don't overfill my trap. Conversely, if I have a teeny itty bitty peak that's not producing very many ions, they could say, okay, well, I need to fill the trap for a longer period of time. So let me let the trap stay open so I get better sensitivity for this itty bitty peak. Does that make sense? Basically, the goal of DFT is not to overfill the trap, but also, if the peaks are very low, to let the trap stay open longer so you get more ions in. Unfortunately, if you set it to dynamic fill time, what you cannot do is the next thing at the bottom of our list here is called Q0 trapping. The Q0, which is that very first quadrupole that's used to focus ions out as they come in from the source, it can actually store ions all by itself. It's too far from the detector to do anything, but it can store ions. And one of the things we talked about when we were talking about a linear ion trap, or ion traps in general, is that they have a fill, close, and scan cycle. While they're closed and scanning, what's happening? I'm losing stuff. It's being pumped to vacuum. Well, this instrument allows you to store those ions that would normally be pumped to vacuum in Q0 for a few milliseconds. And then it releases that pulse. And that pulse is part of the reason why the order of collision energies matters, because they're being held there for a few milliseconds and then released into the instrument. Okay? I think Q0 trapping actually increases the amount of fragments we get, because it increases the amount of 304 that would normally be lost to vacuum is now being held and then releases the pulse of ions that I can detect. You can see here, back to cocaine again. This is a fixed fill time of 20 milliseconds here, and this is dynamic fill time. You see they look very pretty similar, actually. This one has Q0 off, which means while the trap is closed, things are being pumped to vacuum. The top one is the same 20 millisecond fill time, but with Q0 trapping on. So what happens is, as soon as I open the trap, I release a pulse of ions. We start at 10, collision energy of 10. We step to a collision energy of 25, and then we step to a collision energy of 55. And what you see is this pattern right here, which is what I matched to a library. The thing is, our library is built off us doing this for every compound, so that's how we can match it. All right, so we want to set up and build a qualitative method now. We're using MRM as our survey scan. Those are the parent-to-daughter transitions. We have 130 of them stacked together in a method. Each compound is optimized for sensitivity and specificity of the transition ion. We use EPI to generate a full scan mass spectrum with lots of detail to facilitate positive identification. We use standard parameters. That means we set the same parameters and for reproducibility in library searching. Once you set those parameters and then collect the data for all your compounds, you can build your library, and it will work over and over and over. We use information-dependent acquisition, or IDA, to switch between EPI and MRM, MRM and EPI on the fly. I don't have to tell the instrument to do it every time. I want to be able to set up to do that automatically. So, information-dependent acquisition allows on-the-fly software switching between the two MS modes. They're two totally different experiments. One is happening, MRM. Q1 selects a mass, it gets fragmented in Q2, and I look for only one transition ion at the end. Okay, cocaine is detected by me detecting 182 at the detector. Does that make sense? Then I can switch on the fly to a completely different type of experiment where I use Q1 to select only 304. I fragment it in the collision cell, and then I use my linear ion trap to collect all those masses. I close and I scan out and I get a full mass spectra. Then I switch back and start my MRM list all over again. Make sense? What IDA does is it looks at the results of the MRM cycle. It says, okay, you did all 130 drugs. Let's take a look at it and see if it meets my criteria. It determines if any drugs will be selected for a product ion scan, and it determines which drugs will be selected for a product ion scan. We select the most intense peak, but you could select the two most intense peaks. It's up to you. Just remember, for every EPI that you perform, you're costing yourself a second. The instrument switches between those two modes on the fly. Here's an example of our MRM, or our IDA parameters. Yours will be set to whatever your particular needs are. We have a survey scan of 100 plus drugs, about 130. The IDA is the decision maker. When the transition is above the threshold, which our threshold's around 1,000 counts, and it's the most intense transition, in other words, I could have 15 transitions above 1,000. I want the tallest of the tall. And I want to make sure it's not one that I've already excluded. In other words, one that I've said, look, I've seen this 3 times already. I don't want to keep seeing it. Then I triggered the second experiment, which is the enhanced product dyne scan, which gives me a full mass spec. I want to talk a little bit about dynamic exclusion, which is this sort of exclusion list thing where I put it on there for 15 seconds. You saw some of that yesterday. What's going to happen is I'm going to produce 3 product dyne scans at the beginning of my peak. Okay, I think I talked a little bit yesterday about, you may have heard me talk about carosoprol and alprazolam totally co-including each other. This is kind of what alprazolam and carosoprol are going to look like, with the big blue line being carosoprol and the small one being alprazolam. What I'm going to do is I'm going to get 3 product dyne scans for carosoprol, and they're going to occur here, here, and here. Okay, they're going to occur right at the beginning of the peak, because that's when that peak first crosses the green line here, which is my threshold line. Okay, this actually should be pointing to right here. Alrighty. So what I do is say, okay, I want you to ignore that for a set period of time. For us, this set period of time here is 15 seconds. Okay, that's about the width, or about half the width or so, at least, of your average peak. Depends on your LC program. For us, 15 seconds seems to work fine. That means I'm now going to ignore carosoprol for the next 15 seconds. What happens is I can then get 3 product dyne scans of this one right here. Okay, that's my alprazolam. Now I've got a qualitative match for both carosoprol and alprazolam, and I'm going to send that for confirmation for both of those drugs. Whereas before, all I would have seen is an MRM transition for alprazolam, but no mass spectra, or no product dyne mass spec if I had always been doing the top one. Because you can see at no point does alprazolam get larger than carosoprol. Okay, that's the importance of dynamic exclusion. But once I've seen alprazolam 3 times, I want to start ignoring it. So if I had another compound buried under here, I might actually start seeing it. Okay? And what will often happen is on the very tail side of the peak, after my dynamic exclusion for carosoprol has ended at 15 seconds up, it's now fair game again, and I will actually begin to see it again 3 times. Make sense? That's dynamic exclusion. And that's the whole thing in a nutshell right there. Yeah.
The dynamic exclusion is global. You cannot pick each transition.
That's right. What you can do is set up something to permanently exclude after a certain period of time, or always include it. But the dynamic exclusion is, yes, it is global. You set it one time for the entire run. And this is sort of a flow chart of the way the MRM, the way the IDA flow chart works. You start here with your 130, you start here. You start here. The first question asked, this is at the end of my MRM transition, the first question that get asked is, are any of these counts over 11, are any of these drugs over 1,100 counts? Okay, well, carosoprol is over 1,100. Alprazolam also over 1,100. Are any of them on the exclusion list? No. No, none of them are on the exclusion list yet, because this is the first time I've seen both of them. All right, well, do the EPI of the tallest one. So I do my EPI here. So now I've collected an EPI spectra, full scan mass spec of carosoprol. Is this the third time I've seen it? Nope. So if it's not, I go back to here. If I've done it 3 times, 1, 2, 3, then I say, okay, well, I want you to add it to exclusion list. And this is the dynamic exclusion thing I just showed you. And I start back with my MRM transitions, and I go all the way through, and I get to here, and I say, is carosoprol on the exclusion list already? Yeah, it sure is. Well, what's the next tallest one that's over 1,000 counts? Well, now it's alprazolam. Now I get a product dyne spectra for it. And what you get when you add up your MRM transitions is what you see here, and you've sort of seen this already yesterday with the test mix, and that's exactly what this is. You get, at the top is an overlay of all 130 MRM transitions, and you can see there's oxycodone, mepivacaine, there is fentanyl, piroxicam. You see our piroxicam doesn't tail as much as their piroxicam does. We're very excited. Sorry, Kurt. Here's imipramine. This is probably amitriptyline right here, and then there's methadone buried underneath. If you had 130 drugs in there, it would look like a sea of colored lines. Usually there aren't more than about, I think I've probably never done more than about 20 drugs in any one case, which is really a nightmare when you think about it. You get to it and you're just so disappointed. Oh, 20. I'm going to take an hour doing mass spectras now. The second panel is an extracted ion chromatogram of just oxycodone. You get a pretty good idea of its retention time by looking at this. Here, there's 3.02. What you see here is me calculating the relative retention time to mepivacaine. Remember I told you yesterday we put mepivacaine everything we can think of. We haven't quite got it to my coffee yet, but I'm sure we will someday. So that's my relative retention time for oxycodone against a standard that was run probably, by this time, it was probably a year or more old relative retention time. That's what's in brackets. So I've got, I've got a pretty good qualitative match there for oxycodone. The spectras, the MRM transition is very specific for oxycodone. Not very much else triggers it. So I could do that, but I want that one extra piece. I want that product ion spectra. And that's what I have at the bottom. So that's what oxycodone looks like as a product ion mass spec. And you can see there's lots and lots of fine ion detail there. Lots and lots of ways for me to say that is oxycodone and feel confident when I skip into court. And they ask me, how do I know? And I say, well, it's obvious. I know it's obvious because I produced a library match. And this is the library that I built in-house using those very standard parameters that I worked so very hard to optimize. And you can see here, this is oxycodone. And this is the library match of oxycodone that was taken probably 2 years earlier. Looks basically the same. And yesterday I was kind of talking about how the library didn't translate very well, and all you see is the big ions. You can see when we're looking at it, that it actually has lots of detail in there. And you can see this fit number here. I don't even care what that number is. What I care is, do I think that's oxycodone? Yes, I do. I've qualitatively matched it from the product ion spectra. I know it's in the right place in my chromatogram because the relative retention time matters, and it triggered the correct MRM transition. I now can go to quantitate that thing, and I've got my 2 pieces of data. I'm going to walk to court and say this person was under the influence of oxycodone. Or in her case, this person had an overdose of oxycodone. Only the medical examiner gets to write overdose. She just says a lot. And that is what we did to build a method. Any questions from there? Sounds real simple. It took us like a year to get it right. And we tweak it all the time because we always want to make it better. When we find new things, we look and see we didn't realize the instrument would do that, so then we use it or change something about what we learned. It's an ongoing process. We did a lot of discovery to find out how different the new 3200s were from the Q-trap. We found out they're very different. They're very similar. We actually had 3 different instruments. We did all that infusion data on 3 different instruments. We only found 10 transitions, 10 MRM pairs that were different for each instrument. And they were different just really almost from user preference. Did they do midazolam yesterday? You did midazolam yesterday, and when you did the compound optimization, what you probably saw were a lot of ions that were all about the same intensity. So you can imagine it's Tuesday, so one of these ions is going to be a little taller. So it only chooses 4, if that's what you set up as a default. So you can see how it could choose a different 4 based on which one's the tallest at that moment for that instrument. So it will change a little bit, but basically the ions it produces are very similar.